Hello, future engineers. Welcome to my YouTube channel. In this video, I'm going to discuss 3D rigid body equilibrium formulas, equations that may be formulated, and the different categories that you may encounter in a problem. So the principles, 3D force systems in equilibrium. When we set up R resultant summation forces 0, this implies three components of the resultant that must be 0. That is, Rx, summation forces x must be 0, R sub y, summation forces y must be 0, and Rz, summation forces along z must be 0. And this is the equation that must be formulated for a situation where all forces are concurrent. For the general case, aside from these three equations here, and another equilibrium equation, summation of moment equals 0, this implies that summation moment about OX or x-axis 0, summation MOY or summation moment about y-axis is 0, and MOZ summation moment along the z-axis is 0. So again, when the resultant is a couple, this implies that the resultant force is 0. And when the resultant is a force, this implies that the resultant force passes through a point or axis of possible rotation. Then for spring, within Hooke's law, force is spring constant times displacement. And when you enforce moment about an axis, especially for supports with three unknowns, then you can reinforce this equation: moment about an axis equals position vector from moment center to line of action of force cross with the unit vector of that axis. So recall that the moment of a force about an axis, which is a scalar, is position vector RAB cross F, where A is the moment center and B is the point on the line of action of the force, then to be dotted with the unit vector of the axis. So we need this. Then here are the different cases. This clip comes from the book by Beer and Johnson, and we will have also by Miriam and Craig later. So we have a ball on the smooth surface. It is a frictionless surface, or another body in contact with a frictionless surface. There is only one unknown, and it is perpendicular to the surface. If the surface is horizontal, then the unknown reaction force is perpendicular to that, and it should be vertical. Then another situation, when we have a cable, then the force is the tension in the cable. So the line of action of the force is known, and there is only one unknown. Then we have a roller here. Another situation, roller on rough surface. So if the surface is rough, then expect two reaction components, and this is also the same with a wheel on a rail, where this wheel cannot move laterally perpendicular to the rail. So we have two unknown forces or unknown reaction components. If this is the z-axis, so we have an unknown reaction component towards the z-axis, and another one is perpendicular to the surface, rough surface. And there are two force components. Then if we have a rough surface, then expect three component reactions along x, y, and z. And another one, we have a ball and socket joint. And there will be three unknowns, Fz, Fy, and Fx. So three force components for that case. Then another situation, we have a universal joint here. So all the three reaction components are present. There is constraint along x, along y, and along z. Aside from that, there is resistance to rotation along the about the x-axis. So three force components and one couple for this universal joint. So they are free to rotate about the y and about the z-axis. So there will be no moment components about the y and the z-axis for that case, only about the x for this orientation. Then if you have a fixed support, then all three forces are present and all resisting moments about the x, y, and z are also present. So force components and three couples. Then we have hinge and bearing support, radial load only. So forces perpendicular to this uh, axis. So we have Fy and Fz, no along Fx, along the axis of this rod. And there is resistance also about the y and about the z-axis. So two force components and two couples for this situation. Then we have pin and bracket, hinge and bearing supporting axial thrust and radial load. So there will be three forces and there will be about the hinge, about the axis of the hinge, it's free to rotate, so there's no moment resistance about the x-axis if this is the x-axis. So that's why this bracket here is free to rotate about the x-axis, but it cannot rotate about the y. There is resistance about the y and about the z-axis. So we have three force components present and two couples. There's no couple about the x-axis. So for this clip, I took this from Mariam Craig book. So, and we have explanations here, modeling the action of forces in three-dimensional analysis. So type of contact and force origin. So first situation, we have member in contact with smooth surface or ball supported member, and this is the same with the clip from Bear and Johnson. So force must be normal to the surface, except the orientation which is different. Member in contact with rough surface, so we have the two unknown forces. The possibility exists for a force F tangent to the surface or friction force to act on the member as well as a normal force N. So because the surface is rough, then there's a possibility that it is tangent such as F there, not necessarily along Y or along X, but it may be in any direction. Then ruler or wheel support with lateral constraint. So it cannot move along Y. Constraints along Y, it's free to roll along X, so there's no force along X. There's normal force along Z, and there's constraint along Y. So there are two forces. And this is the further explanation. A lateral force P exerted by the guide on the wheel can exist in addition to the normal force. Next, ball and socket joint. So we have here three force components for a ball and socket joint, but it's free to rotate about X, Y, and Z, so no couple present. Then fixed connection, embedded or welded, so all the three forces are present, and there are also resistance about rotation about X, about Y, and about Z. So there will be 6 unknowns all in all for these equations here. Then we had thrust bearing support. There's no force along this direction, there's force, the three forces are present rather, and there's no rotation about this axis here, it's free to rotate because this is a uh, rod that can rotate about this axis here. So all in all, we have three forces and two couples. So thrust bearing is capable of supporting axial force Ry as well as radial force Rx and Rz. Couples Mx and Mz must in some cases be assumed zero in order to provide statical determinacy. So here are the four different categories that we may encounter in a situation. So if we have four system concurrent at that point, so all the three equations, summation versus x, summation versus y, summation versus z, or the x component of the resultant, y component of the resultant, the z component of the resultant must be zero. Then concurrent with a line. So if the forces are concurrent with a line, then still the three equations, summation versus x, y, and z, zero. And because they are acting on the line summation moment about y and summation moment about z must be zero because they are acting on the x-axis. So those are the equations that must be established. Then parallel for systems, summation versus parallel to the x-axis, so summation versus x0, and summation moment about y and about z-axis 0 because forces have no moment about a parallel axis, so that's why there's no summation moment x0 here because it is already understood. Then for the general situation, all the six equations are present. So we have summation versus x0, summation versus y0, summation versus along z0, and summation moment about x-axis, about y-axis, and about z-axis 0. So this is the general situation, and all the problems may fall to any one of these categories, but mostly we have here the general situation. And always remember the supports presented earlier and the number of unknowns per support. First problem, determine the tension in cables AB, AC, and AD. Also determine the tension in cable AB by establishing only one equilibrium equation. So this is the given figure. This is supposedly 3D equilibrium of a particle in space. But we can also solve this by expressing its tension into vector form. If you do not express it into vector form, you solve it by the scalar approach, you can. But the best solution is expressing it in vector form because everything is there, the x, y, and z components. So tension, let's have this orientation. Tension AB is equal to 3I. Magnitude of tension AB, then from A to B, move upward along Z4, along Y -1, and along X +3. So that's why it is tension AB, magnitude of tension AB, quantity 3I along X, along Y to the left, so that's why it's -1J. Then from A to B upward along Z 4K over square root of 3 square plus 1 square plus 4 square. So tension AB is magnitude of tension AB quantity 3I minus J plus 4K over square root of 26. Tension AC, A to C is upward along Z, so that's 4K. Along Y -1, so that's -J. Along X -3 backward. So tension AC is magnitude of tension AB -3I minus J plus 4K over square root of 3 squared plus 1 squared plus 4 squared. So it's the same tension AC quantity -3I minus J plus 4K over square root of 26. Finally, tension AD is from A to D up 4, then along Y +3. So it is in vector form, tension AD is magnitude of tension AB, quantity 3J plus 4K over square root of 3 0 square along X plus 3 square plus 4 square. Simplifying, that's magnitude of tension AD 3 over 3J plus 4K over 5. Then summation forces X0 or Rx0, then we have 3 over square root of 26 tension AB, then plus negative 3 over square root 26 tension AC, then AD has no X component. Since from this equation, then we can say tension AC is equal to tension AB. Then Ry equals 0. So we have negative tension AB over square root of 26, negative tension AC over square root of 26, then plus tension AD times 3/5 or 3/5 of tension AD. Since tension AC is equal to tension AB, then we can express tension AD in terms of tension AB. So 0 equals negative tension AB over square root of 26 minus tension AB over square root of 26 plus 3/5 of tension AD. So expressing tension AD in terms of AB, that's 2 over square root 26 times 5/3, so that's 0.6537 tension AB. Finally, RZ equals 0, so that is tension AB 4 over square root of 26 tension AB plus 4 over square root of 26 tension AC plus 4 over 5 tension AD. Since we have then minus 100, sorry, I forgot. Then we have to substitute tension AC, which is equal to tension AB, and tension AD 0.6537 tension AB. So we can combine these two. So 8 over square root 26 tension AB plus 4/5 of 0.6537 tension AB equals 100. So from there, we can solve tension AB, which is equal to tension AC, and it is 47.8 pounds. Then tension AD is 0.6537 times 47.8. So tension AD is equal to 31.25 pounds. For that challenge question, determine the tension in cable AB by establishing only one equilibrium equation. So let's apply moment about an axis CD so that tension AC and tension AD will not be involved in that equation. So lambda of CD is C to D is positive 3I, 1 plus 3, then that's 4, positive 4J. So 3I plus 4J over square root of 3 square plus 4 square, so that's 5. That's the unit vector of axis CD. Then for AB, so we have to cross R, AD, cross, sorry, R, CB. So RCB cross tension in AB, then that lambda of CD. So moment about CD is equal to 0, and that is equal to RCB. You can also choose RCD if you want, but the simpler is RCD because it is just 6I. If you have RDB, then it should be 3I minus 4J, so it's longer. So we better choose RCB, cross the force. So the first letter here is the point on the axis, and the second letter is the point on the line of action of the force. You can also have RCA if you want, RDC if you want, or RDB if you want. So this is the simpler case. And plus RDA cross the 100-pound force, which is negative 100K. Then that lambda of CD also. So 0 equals components of RCB, which is just 6I. Then 0, 0, components of force for tension AB, 3 over square root 26 tension AB, negative 1 over square root 26 tension AB, then positive 4 over square root 26 tension AB. Then this one is the component of the axis, unit vector of the axis. So 3/5 is 0.6, 4/5 is 0.8, then there's no k, so 0. Copy the elements of the first two columns. Then plus dA is negative 3j, negative 4k. So plus 0, negative 3, negative 4 for dA. Then components of force, 0, 0, then negative 100. This force here, 100k, negative 100k. Then for the unit vector of the axis, we just copy 0.6, 0.80, then copy the first two columns. So 6 times 0, 0, 0, minus 0, then minus 0.8 times 4 tension AB over square root 26 times 6. So there's a value which is negative. Then this is also 0. So there's only one value, negative 0.8 times 4 over square root 26 times 6 tension AB. Then here 0, positive 300 times 0.6, 0 minus 0, 0, 0. So it's only negative 3 times negative 100 times 0.6, 300 times 0.6 is 180. So from here we can solve tension AB in just one equation, and it is equal to tension AC, also 47.8 pounds. You can also compute tension AD in same manner and tension AC in the same manner. A uniform steel plate 18 inches square weighing 68 pounds is suspended in the horizontal plane by the three vertical wires as shown. Calculate the tension in each wire. So for the solution, we have the 68 pound force. Its location is 9, then this is tension A, tension B, tension C. So first we sum up moment about CX so that we can relate tension A and tension B, and 68 and tension C will not be involved. So this is our orientation. Moment CY rather, because this is the y-axis. So by right thumb rule, the positive sense of moment about this axis here, this is CY, is in that sense. So therefore tension B is positive, equals tension B times 9 because this axis is this one, 9 inches, minus tension A also times 9 because this is 9. Therefore tension A equals tension B, or tension B equals tension A. Then, so that tension A and tension B are still involved, then we sum up moment about this axis. This is parallel to the x, so moment CX. By right thumb rule, this is your right thumb, the positive sense of moment is in that direction. That's a positive sense of moment. So 68 is positive, equals 68 times 9, because this is at the center. Then minus tension A times 12, and minus tension B times 18, because this is 18. Since tension A equals tension B, replacing tension B by tension A, so 12 negative 12 and negative 18, tension A is negative 30, tension A to the left, so positive 30 tension A. 68 times 9 is 612. So from here we can solve tension A, which is equal to tension B, and it is equal to 20.4 pounds. Then R vertical equals 0, solve for tension C. So it is equal to tension A plus tension B plus tension C minus 68. So substitute 0 equals 20.4 plus 20.4 plus tension C minus 68. So tension C is 27.2 pounds. So that's the end supposedly. I'll extend the solution by another approach. Let's draw the top view. This is the load location of the 68-pound force, 99. This is the x-axis and that's the y-axis. So for the length of this triangle, this is square root of 18 square plus 6 square. So it is 6 square root of 10. Use your calculator there. For this length, square root of 9 square plus 12 square, so 15. And for BC, square root of 9 square, this is x, and 18y. Square root of 9 square plus 18 square is 9 square root of 5. So we can solve for theta c by cosine law. And we need this distance to this point, 3 square root of 10. It is square root of 3. 9 minus 6 is 3 plus 9 square. So square root of 3 square plus 9 square is 3 square root of 10. This distance, of course, is, because this is horizontal, that's 9. And that distance is square root of 9 square. This is 9 plus 9 square. So 9 square root of 2. So that if we want to compute tension A, we need the angle theta c so that we can compute its perpendicular distance to BC. So by cosine law, 6 square root of 10 square equals 15 square plus quantity 9 square root of 5 square minus 2 times 15 times quantity 9 square root of 5 cosine of theta c. So that's cosine law. You are now in statics, so you are very familiar with cosine law, or you're equipped well with trigonometric equations. So theta c is 63.45 degrees. That's why if you're still weak in trigonometry, this channel is created in order for you to start from the very beginning, static zero, about trigonometry and all other mathematical tools that you need to master statics. So having found theta c, let's call this theta 1, this angle between the 9 and the 9 square root of 5. And this is the perpendicular distance from A to BC. Because if we sum up moment about BC, it is just tension A times that perpendicular distance, which is 15 sine of theta c, this perpendicular distance here, or 6 square root of 10 sine of theta b. Because that's a right triangle, this triangle here. And this is the perpendicular distance of the 68-pound force from distance BC. And it is 9 sine of theta 1. So to solve for theta 1, opposite of it is 9 square root of 2 square equals 9 square plus 9 square root of 5 square minus 2 times 9 times quantity 9 square root of 5 cosine of theta 1 by cosine law again. So theta 1 is equal to 26.565 degrees. Then by sine law, to solve for theta A and theta B, we need that later. So this is theta 2, which is theta c minus theta 1. So that, let's call that theta 3. So by sine law in this triangle ABC, 15 over sine of theta B equals 9 square root of 5 as to sine of theta A equals 6 square root of 10 as to sine of theta C, which we have just solved, 63.45 degrees. So theta A is equal to 71.565 degrees. Theta B is equal to 45 degrees. So moment BC equals 0. By right hand rule, the positive is 68 equals 68 times this distance, which is 9 sine theta 1. Again, this distance from this right triangle is hypotenuse 9 sine of theta 1, and theta 1 is 26.565 minus tension A times this perpendicular distance to BC, which is 15 sine of theta C. So minus tension A, 15 sine of theta C, which is 63.45 degrees. So from here we can solve tension A, which is equal to 20.4 pounds by scalar approach and by trigonometry. Although this is also by scalar approach. So that's a challenge, so that you know how to compute for the perpendicular distance to enhance your analysis also. MAC equals 0, so we sum up moment about this axis to solve for the tension at B. So it is equal to tension B times perpendicular distance, which is 6 square root of 10 sine of theta B. Sorry, sine of theta A rather, because if you have a perpendicular distance here, the hypotenuse is 6 square root of 10 and the angle opposite it is theta A. So sine of theta A. Then minus 68, this distance is 9 sine of theta 2, where theta 2 is theta C minus theta 1. So 68 times 9 sine of theta 2, and theta 2 is theta C minus theta 1. And theta 1 is theta 1, 26.565. So from there we can solve tension B. Tension B is 20.4 pounds. Finally, moment about AB to solve for tension at C. This perpendicular distance is 15 sine of theta A. So let's solve for theta 3 first. So in this triangle here, 3 square root of 10 square equals 9 square root of 2 square plus 6 square root of 10 square minus 2 times 9 square root of 2 times 6 square root of 10 cosine of theta 3. Cosine law in this triangle, so that we can compute the perpendicular distance of the 68 pounds from AB. So theta 3 is equal to 26.565 degrees, which is equal to theta 1. So that moment AB 0, so it is equal to 68 times this distance, which is 9 square root of 2 rather, sine of theta 3, this perpendicular distance here. So it is hypotenuse 9 square root of 2 sine of theta 3. Then minus tension C, perpendicular distance to AB, is 15 sine of theta A. So tension C, 15 sine of theta A, and theta A is 71.565 degrees. It is also equal to, if you do not want 15 sine of theta A, then that perpendicular distance is also 9 square root of 5 sine of theta B. If you want, you can replace this by 9 square root of 5 sine of theta B, which is 45, and the answer should be the same. So tension C is 27.2 pounds. Then another solution is from analgom. I only present in computing for tension A, distance from a point to line BC. So the equation of this line is y equals C is at x is 9, y is 18. So y minus 0, this is the origin B. Y minus 0 or 18 minus 0 is 18 divided by 9 minus 0. So 18 over 9 of x. So y equals 18 over 9 of x. That's the equation of this line BC here. So that 2x minus y equals 0. That's the simplification of the equation of line BC. 68 pounds is at 9, 9, while A is at 18, 6. Take note of that. So distance is absolute value of AX plus BY plus C over square root of a square plus b square. So distance BC, therefore, distance of 68 pound to BC is 2x, 2 times 9, coordinate of 68 pounds, minus y, which is 9 also, y1, over square root of a square, which is 2 square, plus y square, which is negative 1 or 1 square. So it is 18 minus 9, 9 over square root of 5. While the distance of point A to BC is absolute value of 2 times 18 minus 6 over square root of 2 square plus 1 square, and that is 30 over square root of 5. So I will just demonstrate on how to compute for tension A by analogum. So moment about BC equals 0, tension A, its moment arm is 30 square root of 5, then equals 68. This distance is 9 over square root of 5. And this equation, after we cancel square root of 5, is the same as this equation here. 30 TA, 68 times 9, which is 612. So therefore, tension A is equal to 20.4 pounds. You can do it for tension B. I want you to find the equation of line AC. Then tension C, find the equation of AB. And the distance of 68 pounds from this AB here, distance of 68 pounds from AC, so on and so forth, so that you will have another solution. The vertical mast supports the 4 kN force and is constrained by two fixed cables BC and BD and a ball and socket connection at A. Calculate the tension T1 in BD. Can this be accomplished by using only one equation of equilibrium? The answer is yes, because we plan to sum up moments about CX axis, and we express T1 in vector form so that we can find its components. And the components are expressed in terms of T1. So these are the component reactions at A. It's a ball and socket joint, so 3 forces. At C, horizontal along X and along Z components. But we will not name them because if we sum up moment about X, all these forces and reactions or components are not involved. Then T1 in vector form is going down 8 only, going down along Z. Along X, positive 4. And along Y, in that direction, is also positive 4. So T1 in vector form is magnitude of T1, quantity going to the right, so 4I, going forward towards the y-axis, so positive 4J, then going down 10, this is 5 plus 5, 10, because D is 2 meters above the horizontal plane, so we just go down by 8, so that's why negative 8K, over square root of 4 square plus 4 square plus 8 square. Simplifying, so in vector form, T1 quantity 4I plus 4J minus 8K over 4 square root of 6. Simplifying further by cancelling out 4. So T1 is T1, magnitude T1I plus J minus 2K over square root of 6. So that the X component is T1 over square root of 6 in the positive X direction. Y component is T1 over square root of 6 also in the positive Y direction as shown. Then the Z component is negative, so it's going down to T1 over square root of 26. So next is moment about Cx equals 0. By right thumb rule, the positive sense, if this is your right thumb, is in that direction. So the moment of the 4 kN load is positive. So it is 4 times 5 equals 4 times 5. Then this component is minus because it is in that sense. Minus T1, the Y component, T1 over square root of 6 times 2. The moment arm is 2 about X. Then the Z component is also minus because it is in this sense of moment. Minus 2T1 over square root of 6, the moment arm is 4. minus 2t1 over square root of 6 times 4. So combining this, 2 plus 8 is 10. 10 over square root of 6t1 equals 20. So 10t1 over square root of 6 after transposing to the left is 20. So t1 can now be solved in decimal form, 4.899 kilonewtons. So that's it. So the vertical and horizontal poles at the traffic light assembly are erected first. Determine the additional force and moment reactions at the base O caused by the addition of the three 100-pound traffic signals B, C, and D. Report your answers as a force magnitude and a moment magnitude. So 100 pounds downward. So first, obviously OX is 0, OY is 0, then OZ minus 100, 100 is 300 pounds. So these are the positive sense of moment and at O, and these are the component of reactions. And about X also, there's no moment along about Z because the traffic signals are parallel to the Z-axis. So Rx equals 0, so Ox is 0. Ry is 0, summation versus y 0. So Oy is also 0. Then Rz, summation forces along Z. Oz equals Oz minus 100 minus 100 minus 100. So Oz is 300 pounds. Therefore, the reaction at O has a magnitude of 300 pounds. Ro equals 300 pounds. Or simply O, force at O is 300 pounds. Then moment about x-axis equals 0. By right thumb rule, this is the positive sense. So MOX equals MOX, then minus 100 times 35. So MOX is 3,500 pound-feet. Then summation moment about Y, this is the positive sense of moment if your right thumb is here. So MOY, this is 0 because it passes through the y-axis. So My equals 0, so equals MOY. Then plus 100 times 25 plus 100 times 50. This is the moment of this 100 pounds at T is 0. It passes through the y-axis. So MOY is negative 7,500 pound-foot. Therefore, the magnitude of moment about O is square root of 3,500 square. MOZ is 0, as I mentioned earlier, because the forces are parallel to the z-axis. So MO equals 8 to 76 pound-foot. The body is constructed of a slender rod which has a mass rho per unit length. Determine the force and moment reactions at O. So this is the weight of this portion of the slender rod. Density, the length is A, then times acceleration due to gravity G. And its distance from X is A over 2. Take note it acts on the y-axis. This is rho BG, and that distance is B over 2. And finally, this is rho CG. And its distance from the y-axis is B. Its distance from the x-axis is A. So these are the component reactions at O. And the positive sense of moment about Y, about X. There's no moment about Z because the forces or the weights are parallel to the Z-axis. So Rx equals 0, so OX equals 0. So OX is 0. Then Ry is 0. So there's no force in the direction of y, so OY is also 0. So then that's the final answer. OY is 0. Then RZ, summation forces Z equals 0. So we have minus OZ minus rho AZ minus rho BG minus rho CG. So OZ is equal to factor out rho G, quantity A, rho G times quantity A plus B plus C. So for OZ, that's rho G quantity A plus B plus C. So that's it. For the moment, mx equals 0 equals MOX minus rho AG times A over 2 minus rho BG times A, this one times A, then minus rho CG times A also. The distance of rho CG from the x-axis is also A. So factor out rho AG rather. So MOX is rho AG quantity A over 2 plus B plus C. So that's the answer. MOX is rho AG quantity A over 2 plus B plus C. Then MOY, MY equals 0 equals MOY. This is 0. So we begin with rho BG times B over 2. So positive, then plus rho CG times B. So MOY therefore is negative rho BG quantity B over 2 plus C. So that's it. MOY is negative rho BG quantity B over 2 plus C. Then finally, MZ is 0, so MOZ is 0. Those are the answers.